Good morning. Hello, how's everybody? I hope you had a chance to look at the answer key. We can make this a little short today because it is my 21st wedding anniversary. So this is the only class that I'm teaching today. All right, so we're gonna make it happen so I can get out of here and spend the rest of the day with the love of my life. Thank you. Oh, I can't book. Oh, thank you. All right. Well, I appreciate the happy anniversaries, but which question y'all have on the problems? Like I said, I posted them. I think about an hour ago, at least an hour ago. So we can go over those questions. And over the week, for the people that's taking the AP exam, I sit down and remind for what problems to do. Also, when we're done with this, I'm going to post the practice test, and then we'll start a quiz the next week. You didn't do them yet. Cedric, 94. But Cedric, it's okay. So we have 94. What else we got? Cedric gave you 2 days. What am I do with you, man? What else? 94. Anything else? Class? 96. I agree. Gotcha. $97, $98. Okay. 85C. Are y'all trying to gaslight me, man? Give me all these problems, but I'm working them out, though. $87. Yeah. Nope. Nah. Nope. You would say that, Gabrielle. Not gonna happen there, homie. All right. So these problems here, the like 95, 96, 97, 98, 100, it's you got to read the problem and see what type of distribution it is. And that's the biggest thing. Once you do the distribution, so if you looked at the answer key, I showed you what formulas to use. They're not hard. They're not hard, Danielle. Trust me, they're not hard. If you follow the 4 rules for each one of them, well, geometric and binomial, they share the same 3 rules. Okay, only difference between geometric and binomial, geometric, you have to do it until you get a success. So it doesn't count until you get a success. Where binomial, you have a fixed amount of numbers. But the other 3 rules are the same. You got success or failure, data is independent, and all the probabilities of outcomes should be the same in the beginning. All right, 99. Okay, let me see what we got here. Oh, I mean, okay. We'll revisit them in just a second. So we got 99. All right. So we'll talk about the easiest one first. Anytime you do something, all right. So anytime that you do something, you're either going to succeed or you're going to fail, right? That's in anything that you do. So that's one rule. That's a simple rule. Okay, now when they say something is random, they're saying that it's independent, and they all should have the same. When we kept talking about randomness, some being random. So if it's random, that means they all have the same probability of occurring when you start. Okay, so that's the 3 rules. You got a success or a failure. You're gonna check, make sure it's independent, and then you want to check, make sure that they all have the same probability of occurring, which they normally give you that in the problem. And then we're just going to talk about binomial. Binomial, you have a fixed amount of numbers. So they say, well, you did it 10 times. We're going to let you do it 10 times. Okay, out of those 10 times, let's say what's the probability it took you 6 times. Notice it is set until. So until represent a geometric distribution. So geometric distribution, that 4th rule for geometric is it doesn't count until you get a success. So you don't even report it until you write anything down about the data, until you get a success. Those are the rules. Well, we can look at 95. All right. What was it? 95A. We will look at that. All right, now. Okay, so you can do the 10% rule you can use the 10% condition for independence. Yep, you can. You sure can. Yep, you sure can. We're going to get into the 10% condition rule in chapter 7 and beyond. But in a particular case of the problem, they may give you a population, then they give you a sample, and they want to test for the 10% condition rule. But yes, Marie, you can. We'll be using 10% condition rule from chapter 7 and beyond. So they're just introducing you to 10% condition rule and chapter 6. But we're going to use it extensively when we do the other chapters. So that's a good question. Now, but yes, you could do it for independence. All right. So let's start from the beginning. Let's look at 85. Hold on for a second. All right. So for 85, we got the information you got to check to make sure it's a binomial distribution for 8. So we're looking at 85. So 85, first of all, for 85, if you look at the first part of 85, Oh, you said 85C. So let me just look at C then. All right. So if you do C, you know that it's a binomial distribution. So you know you prove that was a binomial distribution when you did A and B, right? Okay. So when you did, so we're looking at 85. So we found that the mean, because it's binomial, the mean was what? 349.65. And the distribution, standard distribution was, what is it? Point. Oh, for C. All right. When you did this for C, are you kidding me? You just want the answer for C? I could give you that answer. So all you had to do, so they told the sample mean was what, 348? And it's a norm curve. Okay, so all you had to do was Z is going to be, what is it, a probability that it's less than? Hold on. All you had to do was do that and solve it. And all you need is a table. So all you need is a table for this. You can look this up. And A for this particular problem is the rules. And they tell, if you read the problem, you can clearly see this by number. All right, so I'm going to go ahead and do 87. So just for the person that asked for this right here, for 85C, just plug that in because it's normal. And then you can just, that's the answer. All right, so let's look at 87. All right, so 87, the independent rule is not meant for 87 because the population is 76 because you have 76 people on the plane. All right, so they told you to ask for the sample, which is 10. All right, so the 10% condition rule states that or you can just do this. You could do n is greater than or equal to 10 times the sample size. Or you can do 1/10 of n is greater than so if I come here and do this, this is 76, and this is 10 times 10, because this is n. Oh, should do it on this side. So I'm gonna do 76, and then this is 10 times 10. And this is for independence. It's not met. All right. All right. So we got 85C out the way. We have 87. So we're good with 87 now? Thelma? I don't see no response, so I'm gonna go ahead and move on. All right, cool. All right, so let's look at 90. Okay. So remember we did let's say if I did N is equal to 10 and P is equal to 0.35. Okay, so if I graph it, it's going to look like, I think it's going to look like this. All right, if I say N is equal to 10 and P is equal to 0.5, it's going to be symmetric. And so if I do N is equal to 10 and I said P is equal to 0.35, then that distribution is going to look like this. All right, so in order, reason why this rule is going to hold, the reason I came up with this rule, because if it's 50%, it's going to be normal. If as it goes away from 50%, it's going to start skewing. So remember, if your sample size is large enough, no matter what your distribution is, if your sample size, as it gets larger and larger, it's going to start normalizing, which is going to be here. So in order for you to find, so it's the sample size get bigger and bigger. So the person that was doing statistics, they did the math and they let the sample size get bigger and bigger. So if we increase the sample size as it get bigger and bigger, although that this is less than 50%, it's going to normalize. And it's going to normalize at that point when your sample size times your success is greater than equal to 10, is at least 10, and at the same time, your sample size and your failure is also greater than equal to 10. Now, if we had a simulation that we was putting in a computer based on this data, if we get the sample size big enough where the probability of the success for each trial times that sample size is at least 10, you're going to see this graph is going, if it was doing this one, you will see this graph is going to normalize. So that's where the normality, that's why that's where this rule comes from. Oh, I'm sorry. My bad. So this is 0.35, 0.50, and 0.65. That's my bad. So if you look in your book, they talk about, I did it the other day, but they talk about if it's 50%, and I had you put it in the computer, in your calculator, where I told you actually what the distribution, and it was symmetric. Then I had one, I think this was 30, I forget which percent I had here. It could have been 40. But So I did. So this is 35. I do the complement. And remember, we looked at the table. The numbers just switched. So when we did the lower end, I think this was skewed to the left, and then we changed it to the complement. It was skewed to the right. But if you get your sample size big enough times the probability, get it to the point where it's going to be at least 10. The expected mean, if it's at least 10, when it get up to 10, it's going to normalize based on the sample size. And thank you, Thelma, for that. All right, so that's number 90. All right, so now we need to look at 94. So if we look at 94, it's a binomial distribution because they told us that the expected mean so they're talking about all the baseball players, the population. So what you want to do, they told us, so the expected mean, they expect all the professional hitters to on average, it's going to be they hit if they have a excuse me, what was that? So 95. So what number is this? 94. I'm sorry. So if we look at that 94, all right, so they told us the probability of success was 0.26, and they told you have a fixed number that a player hits 500, get 500 hits. Then they told us, so we got to find, so it's binomial because this is every hitter that comes up on average has the same probability of hitting the ball, and they have a fixed number of 500. So you're going to you're going to either have a success of hitting the ball or you're going to have a failure. Okay, they all have the same probability of success. Then you have a fixed number 500. And then you could think about it this way. You know there's at least 5,000. If each player get a chance to hit 500 hits, we know that's more than in the amount of baseball players. It's going to be more than 5,000 hits. So that's a binomial distribution. So expected mean is equal to P N times P, which is going to be what, 500 times 0.26, and that's going to give us what? That's going to give us 130. All right, so out of 15 at bats, being have a chance to hit the ball, he's going to hit all the players. These are baseball players going to hit the ball at least 130 times on average out of the 500. Now we got to find the expected standard deviation. So that's the square root of what? N times P, which is 130, times the failure, which is 7.4. Then when we do that, we should get 7.6. What did I do? Let me fix that. So that should be 9.8082. So why did I put 2? Yeah, should have been this should have been 0.74. And then the sample mean was so we said the person we're looking for the probability at that point is going to be 0.3 that a player's going to hit 300, but we got to take that 300. So we got, in order to find this, we just got to do 500 times 0.3, which is going to give us, what's that? What's that's going to be? 150, wouldn't it? All right. So now we want to find the probability that they're going to hit at least, they're going to hit 150. So we got to put at least 150. We can't put below. So it's got to be 150 or better. Okay. So now we got Z is greater than or equal to 150 minus 130 all over 9.80. That's have to change that. So that would be what number was that? 94? Yep. So this is right here. This is your answer. So you have about a 2.2% chance of hitting 300. Which is highly unlikely. Yeah, but Jennifer, remember you got around a 2 decimal place if you're looking at the table. How did I know it was a Z-score? Are you serious? All right. So how I know it's a Z-score? If you do rule for normality is N times P and N times 1 minus P is greater than or equal to 10. All right, so we know that this is 130, right? N times P. This is 130. Then we'll do N. So if we do this, this should be 370. So this is greater than or equal to 10, and this is greater than or equal to 10. Okay, go to your Z-score table and look up. Oh, so it should be 0.4. You're right. Okay, so if I do 204, should be 207. My bad. Well, this is why this is going to be, this is why you're going to use normality. Okay. Yeah, Bree, if I look this up on the table, now you know this is going to be 0.007. Okay. I'm trying to teach you, trying to go through the process. But you know that this is going to be, this is the correct answer. If we got 204, because this math is right. Come on now, work with me. All right, so we get it now. Marie, you understand why it's normality? Yes, no, Marie? All right, so I'm gonna go ahead and move on to the next problem. All right, so the next problem was 95A. All right, so if you do 95A, if you read this problem in, where is it? Boxes. Boxes. Okay, so it said this last sentence said buy all the cards until you have all five. But remember, for the geometric rule, you record when you get the first success. That's not what this is saying. They said you're going to do it until you get all five, but geometric distribution rules tells you that you do it until you get a success. So that's why it's not a geometric distribution. Questions? Because remember, you do a geometric distribution, it starts at x equals 1. So you don't want to just count it when you get all five, because you may never get all five. So you want to do it when you get your first success. All right. So let's move on to the next one. All right. So the next one is what, 96? So for 96, Oh, okay. So if you look at now, if the B part of 95, okay, so the B part of 95, okay, so you have so if you do 95, you have your B, you have your success, or failure. All right, you know it's going to have same probability, and that probability for 95B. Same probability of success that goes, and what was that? That was the same probability of success, your success or failure. Then 3 is independent. And then the fourth one tells you, if you look at the B part, it said Lola decides to keep playing until she wins. Which is her first success. They said until she win all 20. It said until she wins. All right. So let's go move on to 96. All right. So 96, do we need to do A and B or just A? All right, that'll work. All right, so the reason why it doesn't work for A, because if you draw the card, and each time you draw a card, you don't replace it, doesn't the probability is going to change each time. So that's going to negate the rule for all probabilities being the same in the beginning for each one. All right, so that's going to be A. So let's look at B. Okay. First of all, we know the first rule is going to hold. You have a success or you have a failure. You're either going to get it or you're not. Then the second rule is it's going to be, so we know it's independent. Or we're going to assume that it's independent. Or you can use that 10% condition rule if you want, Marie. Okay, now, so then 3, then they say it was picked randomly. Okay. Okay. Then success, same success. Which was what 10%? I think it was 10%. And then they told you the very last part for 96. Lawrence instructor makes him shoot the arrow until he get a success. Oh yeah, for sure. This is my anniversary. We're done. I will put the practice test on the blog tomorrow. It's my anniversary. I'm not doing anything school wise once I'm done with you all. Okay. All right. Now, so this is going to be 96. All right. So thank you. All right. So we're going to move on to the next one. All right. So if we look at 97, so remember for 97, I'm gonna put the rules up here. So because we're gonna use them from now on. So we got the probability if x is equal to k, that's the that's going to be the exact answer, which is going to be your failure and k minus 1 times your success. So we also have the probability that x is going to be greater than k. So that's going to be 1. That's your failure raised to the k. All right. Now, if you're looking for the probability that x is less than or equal to k, that's just simply going to be 1 minus this. It's not in the book, but this is the rule. It's in your old statistics books. So I've done this enough, and you can check. Like I said the other day, you could have checked to see if it worked. All right. You can also use your calculator to check if it works. But if you have these rules, guess what? You don't have these rules committed to memory. You'll use them from now on. You use them in high school, college, undergrad, grad school, and it's a quick way to, if it's a geometric distribution. And also, if you want your expected mean for a geometric distribution, it's just going to be 1 over p. And your standard deviation for a geometric distribution, which you're not going to use, is just going to be p squared. Those are all the formulas we're going to use. Okay. All right. So next thing is going to be, we're going to do problem number 97. All right. So 97, they told us that the probability of success so the probability of success is going to, they want, so they told us that P was equal to 0.2, which is 20%. And we're trying to see when the more is going to crank, right? All right. So we're looking for the probability that it's going to take exactly 3 cranks. Try to crank it 3 times before you get a success. All right. So then we look based on this right here. So you're doing it's geometric. Distribution. So we're looking. So we're gonna do the first time you fail, right? The first and second time. Because remember, geometric distribution starts at x equals 1. Binomial, which we've done binomial. Binomial distribution starts at x equals 0. All right, now, so we got 2 failures. So we're going to do 1 minus 0.2, and it's independent. Because remember, independent is one of the rules. So if they're independent, you're just going to square by how many failures you have. So raise it to how many failures you have. So we got the first 2 was failures. So we're going to take our failure and raise it to how many failures we have. Now, third time is our success. So we're just going to put 0.2 here. So that's going to be 0.8 raised to the second. And that's going to be your failure times your success. Which is going to give us, if I did my math correctly, it should give me 1.28, which is about 1.28%. And that's the A part. That's for A, right? Okay, so we're going to look at that. Now we got to do the B part. But so I'm going to erase this, and I'm going to do the B part. So the B part want us to find the probability that it's going to be greater than 10, right? So all we have to do now is it's greater than 10. So all you want now is your failures. So that's going to be 1.1 minus 0.2 raised to the 10th power. And so that's going to be 0.8 raised to the 10th. And that should give us 0.1074. Now, if you want to, you could take your graphing calculator, go to geometric CDF, let your lower bound be 1, because geometric starts at 1, and your upper bound is 10. Click OK. It's going to give you this answer right here. Good morning, man. I know you hear me talking. Speak up. All right, any questions? Yes, no, maybe? Oop. What's that supposed to mean, Danielle? I didn't wake you up, did I? Okay, outstanding. Let's keep it moving. All right. So that was what, 96? 97. All right, so let's look at 98. All right, so I think you know how to do this one. So 98. So 98A, they asked for, so they told us that the probability of success, it was geometric. The probability of success for 98 was what? 1 out of 6. And then we're looking for the probability that the outcome is equal to exactly 5. So all we have to do, we're looking for exactly 5. So that means our first 4 failures, our first was failure. So we're going to do 1 minus 1/6 raised to our failures. Then that fifth time, we have a success. So that's going to give us 5 divided by 6 raised to the 4th times 1/6. Then that should give us the answer. All right. So if we do that, we should get we should get 0.0804. So I need verification on this. You don't have to eat that big. Go get something. Go get something to eat a little bit later. Oh, you got that? Outstanding. That's why you my Bree. All right, let's do the B part. All right, so for number 98, we're looking for the probability that X is less than or equal to what, 8? All right, so if it's less than or equal to 8, we can use this formula right here. So what we're going to do is 1 minus, we have our failure. So since our success was 1/6, our failure is going to be 5/6, and we're going to raise that to the power of 8. And then again, if you want your graphic calculator, you can check it by doing the cumulative. So in other words, you can do geometric, CDF, and then you're going to do your, so you got to do your probability, and that's going to be probability. You can do 1/6, and then you're going to have a lower bound or upper bound. So your lower bound is going to be 1. Your upper bound is going to be 8. Then that should give you this right here. So, and that should be 0.7674, rounded 4 decimal places. Yes, she is. All right. All right. So this is for 98. If we don't have any questions, we only have 2 more left. I can enjoy the rest of the day with my sweetheart. Now, any questions? She over there sitting on the couch. I can see her smiling from behind. Now, my baby's almost done. Now, all right, so let's look at 99 and 100. All right. All right. So let's look at 99. Okay. So they told you that it took you 1 out of 38 to get a success, right? So that's just your expected mean. So all you're gonna do is just put it's just gonna be 38. Because they said it take 1 out of 38. So for your success, on average, it's going to take you 38 times to get that one success. So that's basically all you have to do for this. I know it sounds simple, but yes, it's that simple. Maybe it's a possibility. Now, I showed y'all a picture of my wife. So showed y'all before we went on break. All right, so now we have to find the probability. So we know that the probability of success is going to be 1 out of 38, right? All right. So what they want us to do is for B. So this is the A part. Then the B part asks us to find the probability that X is less than or equal to 3. For the B part of 99, let me see. For 99, it said Lawrence is learning to shoot. No, that's the wrong problem. Sorry. So 99, it said, would you be surprised if Marty won in 3 or fewer? So that's right. So all we got to do here, now we got less than or equal to, then we simply going to use this formula right here. So that's 1 minus, and since this is our success, 1 minus P is going to be 37 over 38. So we have 37 over 38 raised to the power that we're looking for, which is 3. And then when we do that, we should get 0.0769. Papados? Nah, we're going somewhere else. But Papados sounds good, though. But we're going somewhere else. But I'm going to eat some seafood tonight, though. For sure. All right, so go ahead and look at that problem, see if we got any questions, and then we can wrap up 100. 100 is not going to take us that long. All right. Have any questions? Does it make sense? All right, outstanding. All right. Shabrak, I'm not going to ask you that question because you hadn't done it. Mr. Einstein. All right, so let's look at 100 so I can get on out of here. Okay, now, so your success is 8 or 9. I'm sorry. X is equal to 8 or 9. And that success, that's going to happen 0.097. Guys, if you go back and look on the chart on that page, I think it was 353. Okay, so X equals to 8. That probability for that was, I have to go back and look at it. Then the probability of 9 the probability assigned to that outcome was, if you go back to 353. 051 and 46. Which total was 0.097. So that's our success. But then they want us to find for 100, they ask for the expected mean. So the expected mean for geometric distribution is 1 over p. So this is our success, right? So that would simply just be 1 over 0.097, which in this case is going to equal to it's going to be 10.3093. And that's going to be your A part. All right, now they want us, so you have to be real careful with this one, the B part. All right, so I'm going to go ahead and erase this. I just wanted to show you where this came from. And remember, we can only add 8 and 9 because it was a discrete random variable table. All right, so now they want us to find, if you read the question, let me read it for you. Okay, so for 100, it said, in fact, you don't get an amount starting with 8 or 9 until 40 invoices. So in other words, the probability is going to be X is going to be at least 40. So they say you don't get it until the 40th try, at least until the 40th try. So it's the 40th try and beyond. So that'll be greater than or equal to. Then again, if we go, so for this is greater than or equal to, so this is the same as saying that X is greater than 39. So remember, your X values is going to be integers. So if you wanted to do, so I could just do this, then I could drop down, look up here for my formula greater than. So I could just simply do the failure, which is, so this is P. So 1 minus P is simply going to be 1000 minus 0.097. Oh, basic math. So that's going to be my 1 minus P, which is my failure. All right. So I'm going to do my failure, which is 1903 raised to 39. And then that's going to give me 0.0187. And that's it. What's 123? 123. All right. So this is the B part of 100. This is the A part of 100. So do we have any questions? Well, this was quick. We only took us a little hour. Outstanding. Any questions? All right. What about you, Jennifer, Danielle, Gabrielle, and the rest of you? I'll tell you what. Waiting. Well, I hope this makes sense. You good, kind of, Danielle. What I'm gonna do? What about you, Marie? Jennifer? No. So who is Nike? Is that you, Victoria? Oh, Adenike? Okay. Okay, cool. All right. I'll see y'all later. I got to enjoy the rest of my day. Okay. Took me 23 years to get to this point. All right. So I'll see you all. I sent out, just look for probably tomorrow for the practice test. Then I got to figure out how I'm going to get you to turn in some quizzes and tests. All right. See you later, Bree Bree and Riri. All right. See y'all later. Have a good weekend.